This is the right link. This goes to Teresa's the link Teresa owns, because then she can help me with uploading. Okay. Okay, we're here. And so let's see. So for today, we have talked about a little bit before we start about logistics, and it seems like there's no other things that logistic-wise that we want to talk about. Priya, I'm going to ask Jeff about the process, because since Dr. Omar is also asking me now. Okay, so that's what I'll do. I hope that I can find some time after this meeting. All right. Study group. Let's start with study group, and then we'll do problem solving sessions. So who is going to talk about Priya? Okay, so Priya, can you log in to Tuesday or Fridays?
Tuesday or Fridays.
Yeah. And one question for you, okay, here's Teresa. Good morning, Teresa.
Sorry.
No worries. Okay, let's create that.
Recording in progress.
Okay, so since Teresa has arrived, and we have to set up a little bit. Teresa, any logistic issues that you want to talk about, or we can directly start? Okay, good. And while Teresa is loading up, maybe let's discuss one thing before Priya starts. So last time when we talked about normal mode analysis, when we talk about normal mode analysis, I was sort of assuming that people know about eigenvalue or diagonalization using matrix expression. It probably is not a reasonable assumption because I now I recall when I was doing starting to do research, I saw people do a lot of the matrix notations, and doesn't make sense to me. Well, in fact, I was taking statistics, and the matrix notation get me a lot when I was first looking at them. So I wanted to make sure that things make sense to you. At least not the entire thing, but it's okay to start with small. Oh, I actually erased the important part I wanted. Okay, so last time we were doing this from the force, and the force equal to the mass times acceleration, and we have multiple degrees of freedom, multiple atoms, multiple Cartesian coordinates x, y, and z combined together, and you can, if you write it into a vector form, 1x, well, let's call it flattened index. So you have F1, which corresponds to the first atom, x position, F2, the first atom, y position, so on and so forth. So F3n, you have a 3n column vector. And the mass is, well, as the name suggests, this is the for each entry. So you can actually write this as M1. Well, let me try to do this in a way that let me see if I can do this. Oh, so in fact you have something like this. Okay, and well, to make things a little easier, let's call it R1, R2, which is y for the first particle, R3. So this is basically the full form of what we were intended to say here. So last time what we're trying to do is we're trying to do this. expression. And this expression was used. So we were doing book flow, and we have Hessian matrix. J. So that was from last time. Okay, so from here, do you see this as a matrix multiplication? Is it done for them? So when you have something like this, is it intuitive that you see this is actually a matrix multiplied by a vector? If I do double arrow as a matrix, that makes sense, right? Okay, doesn't make sense. That's fine. It's fine to say it doesn't make sense because this helps me say it more clearly. Okay, so when you have a matrix A1, 1, A2, 1, A12, A22, and B1, B2. What is the matrix vector multiplication? Can anyone tell me? Is it A11, A11, B1, very good.
B12, B2.
Very good. And is that the end or?
No.
No. Okay, so how should I do that?
A21,
Yeah,
V1, A22, V2.
And they form a 2 by 1 vector or matrix, if you would. Okay, so in the end, if you look at it, this is a new vector U. And let me not use this notation. So this is U. U is a vector. And the U is, you have U1 equal to the first one, U2. So this is U1. This is U2. Okay. Okay, so now let's see. It can be proved from linear algebra that when you have matrix multiplication, so let's call this. So you can show that UI, which is equal to the matrix product ith element, is equal to sum J Aij Vj. So the trick to remember it is when you contract two matrix vector or matrix, you are trying to concatenate them or contract the index between them. And the A is a matrix, so it has two indices, row and column index. When you do matrix product, it is a dot product, and the form that we have in the matrix algebra essentially contracts the inner index of the two. So they have to be the same index and then the sum over. So let's look at them and then see if this is the case. So Aij is the little Aij that I'm writing. Maybe I can put it capitalized, but in the end, you get the first element U. So say I is equal to 1. You'll see that if I plug I equal to 1, and then you sum over j equal to 2, j equal to 1 or 2, j equal to 1, and j equal to 2. You sum them. So in the end, this is actually the summation form of matrix product. it satisfies exactly the same algebraic structure that you have when you write down this tabular form of your matrix. And it's actually more convenient to deal with indices with summation, which DeFi, you have seen this in some of our previous derivation. Because in certain cases, if you have more than high dimensional matrices, tensors, you really have no easy means to write them, at least on the board, on the paper. If you have a three-dimensional matrix, then you don't know how to deal with it. But in practice, how you deal with it is to write down this contraction form. Okay, so now observe this. Do you see matrix vector product surfacing? Okay, so in fact, you can write this, and then I'm doing this to show you that this is a vector, and this is another vector. So this is not a matrix product, this is just a single vector. Okay, so what we are doing here, and to make things a little simpler from last time, was we focus on this equation. Is it okay that I erase this? We focus on the equation, and we can easily divide m on both mi on both sides. So you have xi double dot equal to 1 over mi sum j hij xj. And we observe that because summation is a linear operation, so you can any multiplication of a scalar, you can move it in. And we have note that the index is different from j, so you can do that. If you have j outside of the summation, then you have some index issue. So one thing to always check. So now, if we do that, then we get to call this thing another element. Suppose we define it as a ij, which is defined as, well, I think it's clear that it's defined this way. So you get xi sum j, aj, xj. Okay, so that's where we stopped, or where we start to take off and do a lot of matrix operations here. But we wanted to see that this is a vector, this is another vector. So what you're looking at is x vector double dot is equal to a matrix and then another x vector. So essentially, you have some vector equation that you're dealing with. So that was where we were. You'll see that because xi depends on xj, so everything coupled with everything else in general, if you have this kind of equation. So how to deal with this kind of coupled equation? In linear algebra, the typical way to deal with it is to make eigenvalues, eigenvectors. If you think about it, this is the same situation that we're dealing with in quantum mechanics, that if you have basis functions, s orbitals, p orbitals, we know them from atoms, but when you have molecules, if you have well, I cannot help going back to S-Ling. And suppose we only do p orbitals, 1 pz orbitals, then you do know that the two orbitals are atomic orbitals, they are not molecular orbitals. You have to couple them. How do you couple them? This satisfies the Schrödinger equation, so you have to, orbital 1 will be, so all the interactions that you have will couple orbital 1 and orbital 2. And how do you deal with that? You always solve eigenvalue equation so that things become decoupled. So that's basically the idea. And it happens a lot in linear algebra. And you see that shows up in different parts of the field. One of them is Schrödinger equation. The other of them is normal mode analyses. And so essentially, you wanted to ask the question that can I rotate my positions in such a way that I mix them? So we have linear combination orbitals to get multiple orbitals. We have linear combination of positions to get normal modes. So that in the end, what we wanted to do is actually something that can I find u ui equal to the many? Can I find a u in such a way that I have C1, X1, C2, X2, C3n, X3n, linear combination of positions in such a way that my u, only ui, or let me do now I, so that my ui double dot is equal to some form of a in this representation that only depends on ui. So it becomes a one-dimensional problem rather than three-dimensional problem in this case. So that was the idea. And in linear problems, you can always do that. So the process is essentially finding the eigenvector of A. So that was well, essentially this is what we're trying to do right now. So that was the background of that I sort of omitted last time because I was well, I think I did this too much, so I was assuming that it was kind of trivial, but better to make it a little more clear. And okay, shouldn't take more time from the discussion. So the idea is to find it, you basically do diagonalization. A. And we know A is a matrix and it's a square matrix. J also goes from 1 to 3n. So basically you're looking for some unitary matrix and some diagonal matrix which has eigenvalues on the diagonal, and the U is unitary, so that U dagger is equal to the inverse matrix. The columns are also normal to each other, also normal vectors. They are existing. Well, this is basically at the center of linear algebra. So you can always assume that you can find numerical packages to help you to do that. If you have a symmetric or Hermitian matrix, that is mostly what we are dealing with. In more general cases, there are similar forms that called singular value decomposition that you can always do for any matrix that you have. But let's not go into the direction. Okay, so basically that's what we need to do, and those are all matrices. So last time we were starting from there already, or basically I jumped from here directly to there, and then we started doing matrix algebra, and then in the end we found the normal modes. In fact, the normal modes are just the eigenvectors. Those are they are the columns of U, and from there you know how the positions couple. So for instance, if a water molecule, if you compute the mass weighted Hessian, then you'll find that the eigenvectors are going to be corresponding to coefficients. The first one, depending on how you order them, you will see one that is a symmetrical stretch. So there is a one mode that well, basically all three atoms will contribute, but they will contribute in such a way that the two hydrogens are actually symmetrically stretching away from the oxygen. And the second column of U will give you something like a symmetric stretch. And of course, oxygen will have to coordinate in such a way that there is no center of mass motion. And you also have a mode, the third one that corresponds to bending. And that's how you get the normal mode. And there are, because if you do this in 3N, you have to deal also with translation. So after you see a mode that essentially everybody goes in the one direction, same magnitude, a mode goes along the orthogonal direction X, Y, and Z. And you also see rotations that shows up. So those are all going to be the columns of the U matrix. And that's how you get the normal modes. Well, this is a sketch. If you happen to need to do this in your research, then we'll do this by hand. And that's how you get to know how to do this very correctly. Okay, so that was a long comment from from last time, but I think we are ready to go. So Priya, you can take it away from here. I figure that my video has the mirror in the. So let me turn off the mirror. Whenever I update Zoom, they change my setting.
Let's start. Today I'm going to talk about the transition state theory and also how can we apply the transition state or how can we correlate with the DFT. So mainly the transition state theory is why so important is it helps us to predict the reactions rate, and it is applicable to the industry as well, and it's also applicable to our like ozone layer kind of reactions, and also in the material science to find out the defects. So especially transition state helps you a lot. So I'm going to start from the one-dimensional transition state theory. So where the one example is provided in the book, like silver atom, which is diffused on the surface of the copper. So when we diffuse the silver atom over the copper surface, so we can see the different location where the silver can be placed. So in the diagram, you can see in side view, top view, where side view, especially side view at the middle, like the black, that is the silver, which just sit over the one copper atom, which is called on the top. And when the silver atom placed between the two copper atoms, we call as it's a bridge. And when the silver atom sits on the four different copper atoms, it's called the four-fold halosides. So usually the four-fold haloside has local energy minima, and bridge side is the first saddle point, and on top side is the second saddle point or higher energy saddle point, what is called.
So is it clear to everyone what a saddle point is?
No, so saddle point is like it's a point where the actually.
Yeah, very good. Use the board. Always use the board. The best pen is this one.
So this white coordinates is like taken accounted for the E, and I'm going to draw a picture. This is bridging site, we call. So silver. This is silver atom. When usually the silver atom diffuses over the copper atom, it's a bridging site, and when this silver diffuses on two copper atoms, and it's going to change from the on the top. This in this situation, the energy will going to change. So how the energy going to will change? Like it's a transition state, so I can draw like this, just a single point. So okay, I'm going to draw the two transitions. It's not good enough though. It's still,
It is pretty good. It is pretty good.
I'm going to talk about it later, but just I'm trying to clarify about the saddle points.
Right.
So this is the one local minima, and this is the highest energy point. So before getting to this top point, we need to have a kind of energy, not actually the crossing over the barrier of energy, just to from here to here. This is called the first saddle point or first transition state also. And on the top, this is called the second saddle point, or actually this is the transition state. This we call saddle point actually.
Okay, so there's actually maybe Priya, do you know about the saddle point geometric interpretation of saddle point? Okay, so then we should talk about it. So the saddle point language actually comes from geometry, but so I'll first talk about the geometry part, and then I'll try to make connection with what Priya has drawn. By the way, a very nice picture. You're a better artist than I am. Okay, so to understand what is a saddle point, we should come from, well, interestingly, harmonic approximation of the potential energy surface. So when you have energy as a function of, let's consider the simplest case, and when you see my doing simple case with two x and y, you know this one does not show up in one dimension. So you have E0, and let me make the same approximation as Deepa did last time. So we're looking at gradient E to 0 at a stationary point. Station. So when you see the gradient E or first derivative all goes to 0, you are at the stationary point because there's no force. If you're able to sit on there, it will stay. But whether it's equilibrium or not is a slightly different consideration, because people will typically consider equilibrium as a point that is stable. But having the gradient E equal to 0 does not guarantee it's stable. The simple example here is now in 1D, you can have first derivative going to 0. Either you have the minima or you could have the maximum. So when you have a minima, it is stable because then you move it around, it still comes back by lowering energy. If you are at the maximum, it's not stable because if you flick it a little bit, then it goes down the hill. So it's not going to stay. But if you happen to be able to put it on right at the point, it stays. It's stationary. Similarly, if you go for higher dimensions, you also have this behavior, but now your first derivative becomes a vector, and that's the gradient. Okay, so when your gradient is 0, you only have the second derivatives, and then you essentially have the Hessian. Well, sorry, let me not go that far. Let me not go to matrix form. The matrix form is no, the matrix form is well, anyways, let me keep it simple. So you have x. Let me see. I should call it ax squared plus bxy plus cy squared. You have some quadratic form here. Okay. So so what it corresponds to is let's do a contour plot. So suppose that you have this kind of form. You essentially will have some contour plot. If you have a stable minima, then this will be the lowest energy. Or you could have a second case that the center point is the maximum. So that corresponds to directly the one-dimensional case. But there is actually another case that let me see if I can draw it well. Right. Okay. So you can have a case that so let me show you the situation that we were seeing. The situation we were seeing is that there is an ellipse, and you have the ellipse. Ellipse has two semi-axes, and the semi-axes are both. So the second derivative along the semi-axis are both of the same sign. If you have second derivative along the ellipse direction that is positive, then you get minima. If you have both of them going to the negative, then you get maxima. But if one of them goes negative, one of them goes positive, you get something that is called the saddle point. So let me see if I can draw it well. So this look like somewhat like this. So suppose that the first direction for the ellipse, or I don't know how to say I don't know how to say that in plain language, but basically the direction that correspond to the semi-axis are the eigenvector direction, if you would. So those are the eigenvector of the Hessian. That's why it's important to learn numerical linear algebra. Basically, lots of things that we do are eigenvectors. Anyways, suppose the eigenvectors are aligned with the x and y direction, and then you have along the y direction, it looks like minima along the y direction, but it looks like a maximum along the x direction. So your surface will look somewhat like this. It's a little difficult to draw. So it is like maybe easier to think about that way. So along the y direction, you have the surface that look like this, and when you go along the vertical direction, it goes up. So this is called a saddle. Right? It's like what? Oh, I think I read the analogy. So when you're riding a horse, you put some what is that called? I don't know. Saddle. You get the saddle and put down the horse, and that's that direction. That shape is called saddle, and the point where you actually get the zero gradient is right there. It's called saddle point. Okay. Well, took me a lot of time to explain saddle point, but that's the saddle point, and that only shows up when you have more than one dimension, because you need to have a direction that has minima and the direction that has maxima. They coincide on that point, and then that's the saddle point. So in transition state, when you have reactions, obviously you're going to be at the maximum if you look at some reaction coordinate. But it alone, so this is one dimension in the reaction coordinate. There are many directions because, for instance, like in Priya's figure, you have three atoms. You have 9 degrees of freedom with three atoms. So what about other directions that is not in this cube? Guess what? They are supposed to be along those directions. Vertical to the Q should be at the minima, because the intuition is this. The intuition is that how do you get to reaction? How do you get reaction to happen? You well, the simplest case, you have temperature do the job. You wait it long enough, it climbs up, following Boltzmann distribution to the barrier, over the barrier, and because it is the barrier is typically high, so the climbing up the barrier is exponentially difficult. So if you ever goes across the barrier and then go to the other side, you must be going down the road that is the lowest direction, that lowest barrier that you can do. So that's why when you go down, you're actually going through mostly the saddle point if your temperature is much lower than the scale that you have for your barrier. And all the other directions, because you're trying to find the lowest point, so it's typically the saddle point, because you know it's a maximum along the reaction coordinate, and all the other ones are from intuition minima. So that's why it's called the saddle point. I don't know. I don't know if I can make very intelligent comments about first and second saddle points, because I think that's probably from the author's familiarity with this particular system. But obviously you could have different reaction coordinates. That's the same thing. So you have alternative reaction pathways, Q1 and Q2. And from there, obviously you can have reactions, or if they allow reactions, then if you're going from different directions, then they have different transition state, and then they both correspond to saddle points. So the lowest one would be the first saddle point, and then the second lowest one would be the second saddle point. I think that's what they're referring to. Okay, I hope that is clear.
So this diagram shows the relation between the energy and the reaction coordinate. We are just assuming the one direction, the one dimensional. So in this diagram, we can see that the calculated energies for the silver is moving along the minimum energy path between the 244 side of the copper. So here we can see the height of the barrier at the saddle point is around 0.36 electron volt, while the average thermal energy at the room temperature is only around 0.013 electron volt. So it means diffusion is not frequent, always not frequent. So it depends on the temperature or thermal fluctuation that really allows the atom, or we can assume as a silver. So silver can overcome this barrier and make a reaction. So silver atom with a typical amount of energy at room temperature will usually be found very close to the energy minimum defined by the 4-4 side. So I draw this diagram here. So this diagram shows the one-dimensional energy profile, where we can see the two local minimas here, and here. E and B, and this is separated by the X diagram. So from here, the minimum energy is a part of the least energy required for the atom to move from the one side, one transition state to the another transition state. So we can calculate the rate of warping A to B by using this equation, half average thermal velocity into the probability of finding the atom at x is equal to x dagger. So the half means just we are taking an account this region, either this region or either this region. So this equation, we from this equation we need to calculate the average thermal velocity of the warping atom, and again we are going to calculate the probability of finding of atom. So particularly we can calculate the probability of finding of atom at a specific point by using this equation. And also thermal velocity of a warping atom can be calculated by using this equation. Now, combining both equations, we can calculate the rate of warping A to B. So we are going to get this equation. So the problem is this equation cannot be used directly. So we are going to simplify this equation by using the Taylor series. And by using the Taylor series, we are going to get this equation where the last time we also, the professor also tried to correlate with the K and the angular velocity, I think, right? So again, we from the Taylor series, we are going to find the K, and again, we are going to relate with the vibrational frequency. And after that, we are going to get this term, where we can see at the right hand side like xa, when we increase a small amount, that it's going to change a lot in this right side of the equation. That's why we're going to we are not going to take in all the accounts. So this becomes the simplified version. So this simplified version of equation is this. The rate of the warping A to B is just the frequency multiplication of exponential of this term. This is really the same equation, or the same equation as the Arrhenius equation. So we can now find the activation energy and correlate with the temperature and vibrational frequency. So we will get from this equation.
Right. So well, let me ask the team, and so this is an example that how you develop a theory, and as you can see, there's a lot of approximations. I think this may be a hard question to ask, because I'm sort of trying to formulate that in my head while I'm looking at this. So what do you learn from looking at the development of this theory? And this is an open question, so anyone wants to make a comment. So what do you observe during this process? There's no single answer to this, so I just wanted to see if you
just we are trying to correlate all these equations and make a simple version.
That's right. Yes. Well, Priya, you read my mind. So we have to ask a few questions when we see. In the end, this may not be the most important equation for our study, but I typically found it useful when think about what people were thinking when they developed this theory. So one thing you see is that there's a lot of approximations. And you want to connect. So what do we want to connect? We want to connect the figure. So Priya, if you go to the previous slide, we wanted to connect the figure from the reaction profile, some characteristic of the reaction profile, and we wanted to make predictions on what experiment can see. So that's typical process involved in developing a theory, at least in our field. So what is the element? Obviously, there's not. We didn't use the entire reaction profile. What did the person who developed the theory use? What is A and B? A and B is okay. Do they only use A and B?
This is the trying to get the rate of the hopping atom.
That's right. Yes.
Transition atom. Yes.
That's right. So the goal is to get okay. So let's put it in. Let me frame it a little bit because there are too many things flying in my mind. So the theory that they're trying to develop here is they're trying to predict the diffusion of the silver atom on the copper surface. For Bartha, you're going to do something quite similar. We're doing pre-melting. So in fact, there is some literature that we were looking at that did similar things. So what the scope is actually trying to predict what's going to happen from microscopic calculations and even very abridged version, the macroscopic observation of how fast the silver would move on the surface. So that's what they're trying to do. And obviously you cannot, well, in principle, you can do many things ab initio from from first principles. You can do molecular dynamics and really observe it. Okay, that's one option. But back then, when people developed this one, the theory, well, the idea was actually dating back to Arrhenius, and obviously that was before the computers. So how they don't have computers? How do they deal with it? They developed simple theory, and what they're trying to do is they actually try to get the barrier height. Well, this is, I think, the most important thing, the barrier height. So how much energy do I have to go from A to the X dagger? And Bria also mentioned the thermal velocity, which is a little more than what Arrhenius originally have. But that's the two things. So when you develop a theory, what you want to do is not incorporate everything. You want to capture the most important thing. If one, you can capture it right, then it's very good because it means that you actually know what's going on. Well, if you cannot do one, do two. The more you do, the value of the theory lowers. And once you start with that, you want to have some way that you justify why this is the equation, and that's where you see in the next few steps people are doing sometimes not really justified approximations, expansions, and many steps. But you want to connect essential elements, one or two essential elements that you can compute through a set of equations that is not too far away from, not too out of mind, but you can make approximations during the process. and then trying to connect to what the experiment has, so that you need to have something that you can falsify. So scientific method, you need to have something that you can falsify. You're making a hypothesis, and you need to be able to reject it, so that this leads to hypotheses. You test it many times. Make sure that you try to reject it as much as you can, and then if you cannot reject it anymore, you have the theory, and that's one of the process that I see in this nice little example. It actually shows shows this nice example. Does it make sense? Okay.
So, importance of activation energy versus the vibrational frequency in the transition state theory. In this figure, like the solid lines show the predicted rate using the DFT calculated activation energy, where the activation energy is around 0.36 eV, and that estimates the transition state prefactor around the 10 to the power 12 to 13 second. And also the two dash line shows the prediction from using the one-dimensional harmonic transition state theory. The prefactor is similar to the above, around the 10 to the power 12 or 13. And varying the DFT calculation, the activation energy also varied by around plus minus 0.05 electron volts. So here we can say that the small change in the activation energy have much large effect on the hopping rate of the silver than the similar changes the vibration frequency exactly. So therefore, this calculation or transition state theory calculation help us to precise the activation energy is so much critical, and rough estimation of vibration frequency are generally acceptable.
Right. So one thing that you may be asked to do as a computational scientist, particularly if you're looking at the small molecules, people typically ask you to do reaction rates. And this is one of the difficult quantity to get, because in the Arrhenius equation, you have to compute transition state, which is not really the most stable quantity. And when you do that, the error will be amplified by the exponential. Given that because the typical energy landscape is much bigger than thermal energy, so you get this error amplified a lot. So trying to get a reaction rate very accurate is an uphill battle. So don't agree to people asking you to do a reaction rate unless you are forced to. Well, joking aside. But it is one of the challenging quantities, and trying to get it very, very tight is not really always feasible. But if you're looking for order magnitude and estimate within probably 10, within a few order magnitude. So if you predict seconds and then you get hours, you are pretty happy. Then I think that's something reasonable to do. Okay.
So now I'm going to talk about the multidimensional transition state theory. So one-dimensional transition state theory cannot include all the other possible the directions when the atom hopping over the other side. I mean that when the atom changes from here, suppose here silver is going through this path, and when the silver atom crosses the energy barrier point, it may have the different path. Like it has, it may goes to this way or this way. So many directions are possible. So one-dimensional transition state theory cannot include all these possible pathways. So to include those possible pathways, we're going to talk about the multidimensional transition state theory. So you can see this equation. This is almost similar to the one-dimensional. So the main changes is we take into account the directions here. And directions is referred by the vector r. This includes the direction as well as the magnitude. So after this equation, we can see like we are going to simplify this equation again by using the Taylor series, and we are going to simplify the denominator and a numerator. So we will get these equations and this equation, so that all the other possible direction can be included in our the hoping rate.
And you see, eigenvalue equation shows up because of the normal mode. So it's everywhere.
As we did earlier, this is the same equation, but the difference is just we are taking account in different directions, and the hoping rate is here at the B1, B2, like that, and we are going to just talk about the n degree of freedom. So we will get this kind of equation. So this equation mainly tells us about the rate of transition state mainly depend on the activation energy and vibrational frequency of the energy minimum, and also the real vibrational frequencies of the transition state as well. So some of the key insights are precise calculation of activation energy is very crucial for the accurate rate of prediction, and presence of imaginary frequency is also necessary. And multidimensional transition state mainly provides the more complete picture, but in many cases, this gives the similar result as the one-dimensional transition state theory gives.
Well, this one is certainly more than what we can cover for today. But I figure that a few elements that some of us are actually encountering right now worth a little bit discussion. So can anyone tell me what this means, this point? The presence of one imaginary frequency is necessary. It's a necessary condition for identifying the true transition state.
This is the just imagine that you can add the frequency.
So
I think it comes from the literature.
Okay. There's so it is right, and there's a little more than that. So the only person in the room that probably encountered imaginary frequency is Deepa. So Deepa, can you give it a try and explain what is the imaginary frequency here?
This assumption that there is presence of frequency.
You're almost there. When you have a perfect optimization, what happens? Do you have imaginary frequencies?
Perfect optimization? No.
That's right. So when you have imaginary frequency, it means that you are not having a perfect optimization.
To get perfect optimized structures, we need to add some frequency there.
Deepa, you're going deep into this direction. So that's something, some rule that we're not going to cover for now. Okay. So, but Deepa, thank you. This is a good starting point. And I'm glad that we have this figure. Thank you, Priya. So this is one example that we have. Okay. Let me not go this way. So last time we know that frequency is force constant over reduced mass in 1D. And when you have, so this happens only when you have maximum, minimum. And what happens if you have maximum? Guess what? Your force constant will become negative. And when you have a square root of -1, what do you get? A very, very good part, imaginary number. When you encounter a imaginary frequency, it is a signal that some of your normal modes are
that is
actually
negative.
not at the minimum; they are at the maximum. So that is why when you have a perfect optimization, no constraint, no other things, then you are supposed to sit at the minima, and every direction should be minima, so that there should be no imaginary frequency.
So in our calculation, in vibrational portion, we get some imaginary something like that.
That's right. So this is perfect ideal case, but if you have non-ideal case where you have finite steps and so on and so forth, you don't do it perfectly. You can encounter imaginary frequencies, and that direction signals a direction that you go down in energy. So imaginary frequency means that you are in some direction along this particular normal mode, you can go down in energy.
So how can we overcome?
Can you explain again?
Okay. I'm sort of going very fast here. Let me give you something a little bit more appropriate. Okay, and so this is basically perfect spring, and this is the equilibrium. So let me set equilibrium at 0, and then any shift leads to a quadratic increase in energy, and then the force constant is k. So if you do second derivative with respect to x, you get k. Okay, so what is the frequency? Angular frequency. The angular frequency is suppose this is infinite mass wall, and you have a mass here, then you have k over m. Reduced mass of this is infinite plus 1 over m. Also, no index, so reduced mass is m in this case. Okay, so when you see that, you see this is what we understand, and we are kind of familiar with from last time. If you have k that is negative, so if k is 1, let's suppose k equals 1 implies your suppose n is 1. To be simple, you get omega equal to 1. Suppose k is minus 1. Well, nothing stops you from doing that. Not in this situation, but if you have some physical system that you're actually at the maximum, you can always model it with some force constant. So suppose your k is minus 1, then your omega is I, because of this equation. So this example is the more concrete version of what I was trying to do here. And it signals that if you go along the x direction, you go down any direction. So it is a characteristic that you are not at stable minima. Okay.
If we get imaginary frequency, that means we are in the.
That's right. You are not. So you are not expanding. So everything positive frequency or 0, or semi-positive, if you want the jargon, means that your quadratic approximation with positive force constant is a good assumption. But in practice, you may or may not have this thing satisfied, and that will signify as imaginary frequency. And particularly if you have multidimensional system, the normal mode has imaginary frequency is the direction that you can perturb a little bit, and then you get down energy going down. If you have a continuous differentiable potential energy surface. Does that answer your question?
Yeah.
Okay. Okay, so now coming back to that point, why is the true transition state only one imaginary frequency? It is because if it's a true transition state, suppose that you only are corresponding to a single reaction coordinate. You know the transition state has to be a maxima on the transition on the reaction coordinate, but all the others should be only going up in energy. So all the other directions are mini. So at this point, this transition state, when it's not on the reaction coordinate, should be a minimum. And for the reaction coordinate, it's the maximum. And when you have this mode to be maximum, you get the imaginary frequency. And for all the other modes, has to be stable. So you only have one imaginary frequency.
Okay. If we have one imaginary frequency, then we know we have a maximum in our
Yes. I didn't do this mathematical exercise because I don't do vibration a lot. I do molecular dynamics directly. But there are cases that and this is a deeper version of Deepa's question. So we are assuming that we have this and everything else has no linear term. But if you have some linear term, and when you take the second derivative, let me see, this will not stay. Okay, this will not stay. So I think the linear term will not be well. Okay. So for Barta's question is when you see imaginary frequency, you are at the maximum. There's a slight complication here that because you don't really know. Sometimes so when you take second derivative, this term gets eliminated. But also this will lead to instability in the energy. So only when you assume, only when you really have all the linear terms vanished, then you can say it's imaginary frequency correspond to a maximum. But in practice, like in Deepa's calculation, for instance, when we try to do a very big system, you inherently still have some of these terms. So your assumption where you're expanding is actually not really true second order, and there could be other things that leads to this kind of effects.
Computational chemistry was we found imaginary numbers, but
Yes,
I didn't understand.
yeah. So this is actually a very important point because it means that imaginary frequency means dynamical instability. So it means that if you go along the direction, you lower energy.
There may be more than one emergency.
Yes, I'm glad that Deepa, you're asking this question. So everything I'm telling you here is perfect mathematics, but in practice, well, do we have perfect mathematics in computers? No, you don't have perfect mathematics. So let me give you a simpler example. This is the perfect perfect example that you have some project. I'm not a good artist, assume this quadratic. But in practice, if you do DFT calculation, do you get the same number every time?
No.
No, you don't. No. Well, if you do it very, very well, using single core and many other things, so you can get the same number every time within floating point precision. But if you do a lot of parallel processing, which we do a lot, you're going to see that for the same point, you get DFT energies scattering around from different. It's like you're doing experiment. So by doing that, what you're computing using numerical difference is not going to give you precisely what the mathematics supposed to say, and you're going to get noise here. And some of them will translate into, well, noise will be amplified when you do numerical second derivatives. And this will, unfortunately, sometimes give you a minus sign. And so you're going to sometimes see imaginary frequencies. So how do we deal with them? So there are certain range that we consider typically okay. Now we're going into a little bit more practical side. So depends on the system and depends on the system size you're looking at. Depending on you're looking at gas phase or condensed phase, things can differ. And that's why I've been sort of trying to ask you many times what kind of scale that we're talking about. What is chemical bond scale?
1 kilocalorie.
1 EV,
EV.
roughly 100 kcal. What is chemical accuracy? Or I was saying that number. So first I remember this number because when we were talking about it, chemical accuracy, colloquially speaking, is 1 kcal per mole. This one we haven't encountered yet. Spectral accuracy. Can anyone take a guess? Yeah. 1 centimeter inverse.
Mm.
Those are good numbers to keep in mind.
Everything one.
Yes, so basically, when you think about them, why units are important? We want to think things in good units. So when people ask you chemical bond, well, now EV level, and chemical accuracy, kcal per mole, because thermal energy is of that order. You want to make sure you get to that order. Otherwise, as Priya said, that your exponential factor is around 1 kcal. If you per mole, if you don't get this right to this level, then your error will be signified, amplified by exponentially bad. So chemical accuracy, a fraction of kcal per mole. But if you want to give order magnitude, always remember the unit. And spectral accuracy, we're talking about something like IR, and so centimeter inverse. These units help you. So I sort of hinted at this IR, and when we're doing vibration, what kind of accuracy are we talking about here? Which one is vibration?
S spectrum.
Yes, spectral.
So ideally, you want this level of accuracy, but in practice, your DFT is limited here.
Mhm.
Can anyone tell me how much 1 kcal per mole is, centimeter inverse? Well, I also don't know that. I actually know that number. I think it's 30 something. Oh, I was wrong. 300. Yeah, as you can see, I don't remember things. So this is around 300. Okay. So you cannot get much. Well, you cannot really get centimeter inverse accuracy with DFT. So what do we do here? Well, when you do vibration, the good thing is that because you are doing systematic trends, so you can actually get away with better accuracy than 1 kcal per mole. So typical rule of thumb is if you have imaginary frequency, and I'm talking in condensed phase settings, condensed phase, you should be able to get a little better than condensed phase because your system is smaller and your DFT functionals are typically more converged. Generally speaking, if you're looking at, suppose the imaginary frequency 10 centimeter, 10i, not too bad. You can probably ignore.
Sometimes we can get 2 or more than 2.
That's right. Yeah. So it's a borderline. So depending on the system that you're looking at, well, I would be still confident that if it's 20, 30 centimeter inverse in imaginary, I think that's probably okay. People are doing molecular quantum mechanics there, so 10 probably okay. But your system is huge.
Yeah.
one of the bigger ones than what people typically deal with. So you can probably get away with that a little bit. But as you can see of this order, in solids there are some rules that you can apply, which is something that we were sort of alluding to, that you can ensure that you have the translational modes and the rotational modes accounted for. So that's called acoustic sum rules. And by applying them, this can eliminate some of the issues. Solids are more sensitive and because there are a lot more modes. So it's generally more difficult to get to this level. But certainly you don't want to have 300 centimeter inverse in the imaginary frequency. It is a bona fide direction that one should refine and reduce the error in the structure. Okay, so this is a little bit more on the practical side and then some experience, and also depends on what the system you are dealing with. But general rule of thumb is roughly like what I just said.
Yeah, that's all.
Okay, very good. Yeah, it is a
But I have one question.
Yeah.
It is written that the first transition state of the first derivative is always 0 somewhere else in the book. I didn't get it exactly.
So which form?
No, there is not written, but inside the book.
Okay, so say that again, please.
First transition state of first derivative is always 0.
Yes, so for every transition state, the first derivative will be always 0. So do you mean first derivative with respect to reaction coordinate?
Yeah.
Yes, so because so it's one of the definition for max Singapore.
Like how can we connect with the chemical reactions?
Okay, so it is more like the geometric description. So when you have a transition state, and again, I'm coming from more on the dynamics side, so I feel this is a little bit limited description. But when you don't have choice, or when you don't have a lot of means to get all the details, as we were drawing on the board, we don't have any numbers from the computation. It's difficult to get them. So when you want to characterize the curve with minimal data, what do? You want the critical points. Critical points are typically the ones that has minima, maxima, so on and so forth. And so that's what they did. They wanted to use only the minima, which are the starting materials or the product, and the maxima along the reaction coordinate, that is transition state. And from there, they build a simplified theory rather than studying the curvature around each point. Because, well, first of all, it's not clear that there's only one. And then another one is it's not clear that what we have in a defined reaction coordinate is always the best one. So when there are so many uncertainty, people want to simplify and get the theory first. So here comes that. Well, once you choose the critical points, they have definitions. The definition is gradient E0. So that's the definition of these critical points. So the fact that dE dQ at the transition state is 0 is because they have chosen a single point to represent this region. Because using a single point is easier to deal with than many points. And so in some sense, it's kind of by definition that it is a property that one should expect for transition state.
Can we read it as a stable point?
Okay, so stability correspond to what I'm glad we talk about. So stability correspond to the mode we're talking about, and it's going to be unstable well, I think the figure shows quite clearly that this point is unstable. If you flick it, it will go this side. If you flick it this side, it will go back. So it is unstable along the reaction coordinate as it needs to be. But it's supposed to be stable along other directions that's orthogonal to this reaction coordinate, which you do have 3n minus 1. Well, removing the translation, rotation, rigid ones, and you do have the remainder degrees of freedom that needs to be there, guaranteed by linear algebra. But they should be stable directions. So if you go along direction that's not along the Q, you are going to get energy increase. So that's what the this point is about. Did that answer your question, Priya? Yeah. Okay, very good. All right, so we have probably around 30 minutes. Does anyone want to propose a problem that we solve? And I can make it clear here.